Okay. Last time we talked about resource-bounded computation. Up to this point in the course, we talked about whether something is possible or not possible. Things are decidable or not decidable. And in fact, we even distinguish between degrees of undecidability, Turing degrees. And we saw that some things are more undecidable than others. And then we started to split hairs about resource usage, how much space or time things take, given that they are doable, possible, decidable. And that's where things get tricky, because now we watch the clock. We have a stopwatch, and we measure the allocation of time or space or other resources. And we said that something is decidable, a language is decidable within time t of n if there's some Turing machine that decides it, that accepts or rejects each string in sigma star within time t of n steps. N is the size of w. Right? And same for space, the analogous definition for space. Something is decidable within space S of n if there exists a Turing machine that decides it, accepts it within that space bound, guaranteed upper bound. So these are upper bounds, are big O, so they ignore constants. And we defined several families of complexity classes: deterministic time, non-deterministic time, deterministic space, non-deterministic space, parameterized by whatever function t or s, time for t for space, s for t for time, s for space, and these are sort of analogous families of decidable languages. So these are properties basically, and we said that, and we said that each one of these time classes for non-trivial functions, they're not just full of interesting languages, they contain an infinite number of languages each. And there's an infinite number of classes, and each language could be infinite in of itself, containing an infinite number of strings. So now the types are getting 4 deep or even 5 deep if you consider that there's a lot of these classes, infinite number. We said that time is tape dependent. If you have more tapes, you can be more efficient in time because you can use a tape as scratch and copy things onto them and then compare them to the original tape where they were sitting on originally, the data, and thereby save some time. So time is tape dependent. Space is tape independent. We mentioned that you can take the tapes and then merge them into a single tape using dovetailing technique, and basically you can interlace the tapes into a single tape and you don't lose any space by doing that. 3 times as much space is the same as 1x times the space. Asymptotically speaking, they're equivalent, modulo a constant. So space does not depend on the number of tapes, but time does. We also mentioned that a one-tape Turing machine can simulate an arbitrary k-tape Turing machine with a loss of at most quadratic, and sometimes you can even do better than that. Right, so we said we can't use more space than we have time to use, and if you have more space and more time, you're better off. You're not losing any languages, you're only gaining languages that you couldn't recognize or decide before. We said that you can place certain languages in certain space and time complexity classes pretty straightforwardly. Like 0 to the n, 1 to the n, you can recognize in quadratic deterministic time, or in linear space, or in logarithmic space even. And you can reduce a time from quadratic to n log n deterministically by erasing every other one and every other 0 and so on, halving the number of each in every phase. So we know it gets down to algorithms. How clever can you design algorithms to use less time or less space? That's what algorithm design is all about, except now we're doing it for Turing machines. And if you have more tapes, you can be better off. So sigma star, for example, could be recognized in linear time simply by simulating the finite automata. And in fact, every regular language is in linear time by the same reason. You can just simulate the finite automata that accepts that regular language. It's also in deterministic constant space. Why? Because the finite automata doesn't use any extra space. If it used a lot of extra space, it wouldn't be a finite automata, it would be a what? Turing machine, right? So every regular language is in deterministic constant space. So these are simple theorems. Soon the theorems will not be so simple. So for example, $W, you can recognize it in quadratic time by going back and forth from one W to the next, marking as you go, comparing the first W to the second W. And you can do all that in linear space as well. And if you want to get clever, you can do it in deterministic logarithmic space by keeping a counter of how far into the first W you are, and a second counter that much into the second W. Compare the bits or characters pairwise and keep doing that as you increment W, the position in W that you're in. And that requires only a few counters of size log n, because you can represent numbers of magnitude n using only log n bits. Okay, so that's even more thrifty use of space than doing it in linear time by straight marking. How many understand that strategy? Okay. So we define special time classes that we use so much that we give them special names. So P is defined as the infinite union over all d time for any polynomial, d time n to the k for any k, infinite number of polynomials of arbitrarily large degrees, union them all together and you get P. So this is the P that we know and love from P is equal to NP. This is the classical polynomial time recognizable languages or computable functions. And P is robust, it's model independent. So the same P and the same NP hold for not just Turing machines and not just any number of tapes of Turing machine and any modifications of Turing machines, but also for Dells, for iPhones, for supercomputers, and for abacus. Even primitive slow devices for computing like an abacus still has the same P and NP as all these other models of computation. So it's very robust classes. Right? So if an alien race of beings once, one day will come to visit us, even if they've been around for 1 million years, chances are that their P and NP for their computers, which we don't even know how their computers will look, chances are it'll be the same class P and NP. Okay, they're very, very fundamental, robust, model-independent classes. That's why we harp on them so much. All right, so very easy to see that P is subset of NP. Why is P a subset of NP? Because determinism is a special case of non-determinism, right? For non-determinism, you have the option of branching out, right, and bifurcating and going to multiple states simultaneously. The option, but not the obligation to do that, right? So with determinism, you're obliged to only be in one state at a time. So NP is a superset of P. P is a subset of NP. But whether it's proper containment or not, we don't know. That may be equal. And that's literally $1 million question. The Clay Institute of Mathematics has a Millennium Prize worth $1 million cash, 7 different problems. One of them is whether P is equal to NP. One of the problems was already solved, and the guy who solved it didn't want the $1 million, amazingly enough, but they're good for their money. So classical problem has been open for 45 years, likely to be open for a lot longer for a number of technical reasons, not just historical reasons. Similarly, we define P-space as the infinite union of the deterministic space n to the k for all k. So this is all polynomial D-space, all polynomial deterministic space classes, all union together. Together they give you this class P-space. Remember, these are all properties still. P is a property, NP is a property, P-space is a property. And all these individual D-spaces are properties too. And so P-space is basically deterministic polynomial space. And we can define NP-space as non-deterministic space that's polynomial. The union of all those together give you NP-space. By the way, stop me if you have any questions, because right now we're still on definitions, but very quickly definitions will become theorems, and these theorems will become non-trivial. They'll become very deep very quickly. But it's very important to understand the definitions crisply and clearly and without any hesitations. And then we can start going into deeper stuff. One can't simply walk into Mordor. You have to do it cautiously and with all the right definitions in mind and be very comfortable with them. Okay, so easy to see that P-space is a subset of NP-space. Why? Because again, determinism is a special case of non-determinism. So you can do it, deterministically. Certainly, you can do it non-deterministically in the same resource bound, whether it's time or space. Of course, the other way around, it's not so obvious. It turns out that deterministic polynomial space is the same as non-deterministic polynomial space. That one is not as obvious. In fact, we will prove it later on. It's a consequence of Savitch's theorem. It's a theorem by Savitch, and it's not trivial to prove. This is the case. But this is the analog of p is equal to np, except not for time, but for space. How many get that? This is the analog for p is equal to np. Right? For time, we don't know if it's true. P is equal to np. It's open. For space, this is the analog. Polynomial space, deterministic polynomial space, is the same as non-deterministic polynomial space. That we can prove, and we will prove this, probably today, actually. If we get to it, we probably will. Any questions so far? Okay. So a few more definitions. Exponential time is the infinite union over all exponential deterministic time classes, n to the 2 to the n to the k, so 2 raised to any polynomial. So we allow quadratics and cubics in the exponent. It's not just 2 to the n, it's 2 to the n squared, 2 to the n cubed, any polynomial that you'd like in the exponent. Union them all together over all polynomials, and that's your EXPTIME, exponential deterministic time. And similarly, exponential space, the union of all deterministic polynomial space, exponential space classes. So that's EXPSPACE. And of course, you can define also logarithmic space, this deterministic space log, or deterministic logarithmic space, sometimes called LOGSPACE or simply L. L just stands for that. Okay. There's also multi-log space or polylog space, and it's powers of logs. But I'm not writing it down on this slide. Non-deterministic log space is, again, non-deterministic space that only uses log amount. Non-deterministic computations in log space. By the way, I mentioned it last time, but let's say it again because it's important. What's the definition of when you compute non-deterministically? What's the definition of your time usage? Because all these different paths going on simultaneously, some will accept, some will reject, some will run forever. So how long does this take, non-deterministic computation, time resource usage? Well, what is the time of this big non-deterministic tree that's going on? How would you define it? Would you look at the shortest path, the longest path, the average of the paths? Shortest. The shortest accepting path in all cases, that's your time. Space, how would you quantify the space usage? Whatever the shortest amount of space that the accepting time, the accepting path, the minimum accepting path will yield. So that's just for the record. All right, so let's look at some more theorems, and they'll get more and more esoteric as we go. And they'll be harder and harder to prove. Okay, so first, an easy one. Deterministic time F is inside deterministic space F. That's true because why? How would you prove that? It's easy. It's almost a trivial observation, but you got to say something. So why is that true? Why is every language that can be recognized in deterministic time F of n can also be recognized in deterministic space F of n? Yeah. Yeah, it takes time to access space. So if you have a space bound, that's even better than a time bound of the same quantity f of n, right? Because you can't use more space than you have time to use that space, right? If your house has, more room, if your mansion or castle has more rooms in it than there are, nights in the year, days in the year, you can't possibly be using all these rooms, right? Constructively. So space is better, more useful than time if you have a certain bound on either one of the same quantity f. Another way of thinking about it is space is more useful than time as a bound because it's reusable, and time isn't reusable. Time is not a reusable. Think about it. If you have a certain amount of space, you can clear it out and reuse it for some other computation or for the rest of the computation, clear it out, reuse it again and again and again. But time you cannot reuse like this. Every second that passes is gone forever, right? So if you ever find a bottle with a genie in it and the genie gives you two choices. You can have, you know, a bound of your choosing and say, you know, you can have at most $10,000 in your account at any given time, ever, or you can have 10,000 days left to live. You know, which bound should you take? And if you take one bound, you're not bound by the other bound. You're not really constrained by the other bound. So which bound would you rather have on you? You can never have more than $10,000 in your account at any given time, or you cannot have more than 10,000 days left. Or even 10,000 hours, let's make it more dramatic. 10,000 hours or $10,000. What would you rather be a constraint on the rest of your existence? It shouldn't be hard. What? Yeah, take the dollars. Take the dollars constraint. Why? Because $10,000, you know, it's a lot of money still in your account, and you can always make more if you need it. So if you deplete it down to $5,000, well, you know, work a little bit, and then you'll have another few $1,000s. But if you only have 10,000 hours left, that's not a lot of time. It's not a lot of months left, right? So, so take the money, right? Not the time bound. Kind of reminds me of this old joke about, you know, a guy finding a genie, and a genie says you can only have one thing. You can have infinite money, or you can have infinite wisdom, but one or the other, you can't have both. Take your time and decide. And the guy, you know, thinks very, you know, kind of feels philosophical and lofty and righteous, and, you know, doesn't want to be greedy. So he says, okay, I'll take infinite wisdom. And the genie goes boom, and the guy is infinitely wise all of a sudden. He pauses for a few seconds. He goes, damn, I should have taken the money. So, you know, when a resource is reusable, you're good, you know, and it's a more useful resource. So that's why we have theorems like this that are pretty obvious, right? And you can refine it. You know, it's because of this reusability. In fact, you can bound d time, deterministic time f, by deterministic space f over log f. So you don't even need all that f in terms of space to still be able to do whatever you can do in f time. Okay, so this is harder to prove, actually. You have to be able to simulate deterministic time more efficiently with less space. But this is a true theorem. This is harder to prove, and the first is trivial, the second is not trivial. All right, here's one. We will prove this one, and that's not that bad to prove. Non-deterministic time f is inside deterministic time c to the f for some constant. Question? Well, they're different bounds. But what we're saying is that all these apples are fitting inside this big orange cart, is what we're saying. Because remember, we've seen examples, right? Space and time are two different resources, but we already saw plenty of examples here where this language here, 0 to the n, 1 to the n, was in deterministic quadratic time, and at the same time, it was in deterministic linear space. And simultaneously, it was in deterministic n log n time. So, you know, we placed it in several different classes. So yes, it's apples and oranges, but every language falls into lots of these classes and doesn't fall into others, right? Try to recognize this in constant time or constant space, ain't gonna happen. In fact, we know it's not gonna happen in constant space. Why? Because it's not regular. It takes a stack. It's a context-free language. It's not regular, 0 to the n, 1 to the n. And why is it not regular? What's the proof? One word? Pumping. Good. So you see here, we're putting, for two tape Turing machine, we're putting it in linear time and also in log space. Okay, so we're putting certain languages into different space and time categories simultaneously. And then when we have theorems of this form, here, it means anything that can happen in f time can separately also happen in f space. Any language that's in here is also in here. So here it's not apples and oranges anymore. This is a set of languages. this is a set of languages. We're saying this is a subset of that. That's not trivial at all. Here we're saying this is a subset of this, which means this space resource is more valuable than this time resource because of this reusability, and that's how much more valuable it is by at least a log factor. Right? So you don't even have to have the same amount of space to do whatever you can in the same amount of time. Even if you have that space divided by log, you're still good. Everything that's in here is also in here. Okay? And here we're saying everything that's in non-deterministic time f is in deterministic time exponential in f, where the base is c. C can depend on the language. Why is this true? This is not obvious. Why is that whenever you have non-deterministic computation, you can replace it by a deterministic computation that does exactly the same thing with at most an exponential penalty. You're only going to pay exponentially. Now, exponential is, don't get me wrong, it's a hefty fine to pay. But it could be worse. It could be double exponential or triple factorial or some worse thing than exponential. There's plenty of things that are much worse than exponential, like a stack of exponentials with the n at the very top. Power set. Close. So for finite automata, we have a power set construction, and that's the intuition. And you have an exponential number of states. You have an exponential explosion in a number of states. And those exponential states keep track of all possible subsets of the original non-deterministic computation. That's a power set construction for finite automata. Here we're talking about Turing machines. So you can't just play with the states. You have to worry about the tape, right? And the tape becomes part of your meta state, right? Whatever the tape contents are, that's part of your meta state. It's not part of your finite control where the real states are, right? But it's part of your kind of overall state. Plus the read-write head position on the tape, that's part of your state too. Okay. So basically, you take this non-deterministic computation tree that bifurcates, and you simulate it deterministically, breadth first search, one level at a time as you expand it, right? And you're using f space on the height of the tree. Height of the tree is at most f. That's why we have f here for the non-deterministic. We already said that the shortest path is f, right? That's how much time you're incurred non-deterministically. But as the tree goes deep, it can also go wide. How much wider it is than deep for a tree that has a branching factor of 2 or 3 or c in general? Exponential. So if the height is f, the width of the tree is c to the f for some branching factor c. And that c can depend on the maximum branching factor in your non-deterministic computation. If it's 2, then fine, but it could be larger than 2, but it's a fixed constant. How many get the proof now? Okay, any questions about that? So you basically brute force simulate all paths, and it's going to take a lot of space because you're going to keep copies of all these different branches of the computation, and you're going to invest a lot of time doing that, but that's okay. You're paying for that in time. So anything that you can do in non-deterministic time f, you can do in deterministic time c to the f. So it's the analog of the power set construction, but now you got to keep track of not just states in your finite control, but the actual complete contents of the tape and the read-write head as well. Okay, we're good on this theorem. So this was not completely trivial here, and they'll get more and more subtle as we go. Right? So here's another theorem. D space f of n is in d time c of f of n. So you were saying anything that you can do in deterministic space f, you can do in deterministic time c to the f. And it's a similar construction. Right? So a computation can expand, can occur in deterministic space in a big block of space of size f of n. By the way, n is always the input size, right? So it's a function of the input size. So you have a big block of space f of n, and whatever happens in there, you can simulate it and simulate it and simulate it, and at most you'll have to simulate it for an exponential amount of time before you'll know what the outcome of this space-bounded computation is. But there's a catch here. the space-bounded simulation, the space-bounded computation here may never halt. If you're time-bounded, you cannot run forever, because then you wouldn't be time-bounded. If you have a limit on your time, at some point you have to stop and respect that limit. But if you have a limit on your space, you don't have to stop, because you can still compute within the space-bound, and space-bound could be very generous, like a gigabyte, and you can keep churning and churning and churning and run forever within that space. How many get that? Okay, so how will you know when that thing will run forever? If it repeats. And how do you know if it repeats? If you're a simulator. You already did the hard part. You said find out if it repeats. The easy part is, how will you know if it repeats? Yes. Which concept did he apply implicitly without saying it? Let's say it. The problem lemma uses that principle too. Pigeon-hole. How many see pigeon-hole here? Yeah. So within that space, you can churn and churn and churn, but after a while, if you're going to stay within that space, if you churn for billions of years and trillions of years, eventually you'll repeat yourself. Even if it's a large space, like a gigabyte or a terabyte, eventually the same pattern will occur again, because you're deterministic. And if that space pattern ever repeats, the exact state is re-entered a million years later, what will happen after 1 more million years? Again and again and again, it'll repeat and repeat and repeat. And it'll run forever. So you as a simulator can detect that. How? Keep track of all the states that this thing has ever been in. And yeah, this will take a lot of time. So for every state change that this does, look at the entire history of all the states this was ever in and see if it's equal to any one of them. And that's a lot of work, but you could do it. And eventually, you'll know if this ever repeats, and if it does, you'll know it runs forever. And if it runs forever, you know it will not accept. And if it doesn't accept, you can just stop and accept. And so you're doing in exponential time what this thing will do in linear time, linear in f. How many get this concept? It's important, because there'll be cases of this that are a lot more complicated than that, and they're coming up too today. So, any questions about this? So you're simulating arbitrary deterministic space-bounded computations using a lot of time. Here, there's no space-bound. Here, you're also using a lot of space. But in particular, you're using a lot of time to do this. You can also bound the space. So you don't have to use exponential space here. OK, so that's why deterministic space f is in a subset of deterministic time c to the f. And that c depends on the alphabet size, on the particular language you're recognizing. It depends on a bunch of different things. Question?
Why do we need c to the f? If there's any state repeated in d space f?
A good question. Why do we need that long to see if this repeats just once? Yeah, because this can go through every possible configuration of the space and avoid repeating for at least that long. Let me give you an example. Let's say this just counts. 1, 2, 3, 4, 5, 6, 7. All it does is counts. And it has n bits of storage. And it's using a counter of n bits. N could be a billion. It could be a gigabyte or a terabyte. All it does is counting. 1, 2, 3. 1 is different than 2. 2 is different than 3. So all the states are different. When will it ever repeat? When the counter cycles around. But that will take how long? If you have n bits, how long before the counter resets to 0? Or resets to something it's been before? 2 to the n. And it could be as bad as 2 to the n. All I'm doing is counting. I'm going through different states for 2 to the n different states until finally I'm forced to go back to one of those that I was before. And now I have no choice. I've exhausted all the possibilities. And this has to keep track of all of this, and that's how long it takes. Yeah, it's a good question. And a counter is just a simple example. It could be much more complicated and subtle than that, but I just give you an extreme example where that many state changes are possible, and they're all unique. Okay, question? So it's not, this C is not quite the same as this C. This C is a kind of a function of the non-determinism, like the branching factor and so on. This C, there's no non-determinism here. It's deterministic and deterministic. But what about the alphabet? When I said counter, I'm counting in binary. So 0, 1, 0, 0, 1, 0, 0, 0, 0, 1, 1, 0, 1, 1, 0, 1, 1, blah, blah, blah. So I'm counting. But what if the alphabet had 3 characters? A, B, and C. Or just 0, 1, and 2. So I would be 0, 0, 0. 0, 0, 1, 0, 0, 2, 0, 1, 0, 0, 2, 0, and so on and so on. So if I'm counting in base 3, how many different values are there for n digits in base 3 of all possible combinations? 3 to the n. So C will be 3 now, not 2. And if it's something bigger, well, that could happen too. So that C will depend on the alphabet size and also on other things. It can depend on the language itself and the read-write head positions. But we're just throwing a C there, so it's not just necessarily a 2 and only a 2. Yeah. Is this a corollary of this? Of this? No, because the second one puts a time class in a space class of smaller size. This one puts a space class in a time of larger size. It's different. You see, it's this one is kind of apples and oranges, or here. Here? So this one basically is a more efficient space simulation of a certain time bound. So here there's no C. Or look at it differently. Here the C is fixed, and so it gets lost in the asymptotic notation of the big O. Yeah. Here the C is not. Here the C is not necessarily fixed across all possible functions. Here the C is fixed. Here C doesn't depend on the function or the alphabet size or anything else. Here the C does, and so it's got. Because not all C's are created equal here, even asymptotically. Because 3 to the n is asymptotically bigger than 2 to the n. How many get that? 3n is not asymptotically bigger than 2n when you just have multiplication of the 3 and the n and the 2 and the n. So 3n and 2n are the same asymptotically. 3 to the n and 2 to the n exponentials are not the same asymptotically. In fact, you can think about it this way. 2 to the n and 4 to the n are not the same asymptotically because why? Give me a simple reason. 2 to the n and 4 to the n, they're not asymptotically the same because why? Prove it. What's that? How much faster? How much? 2 to the n times faster. Say it slightly differently. So it's very, maybe 2 to the n faster for exponentials. Is it the same? Quadratically faster. One is the square of the other. That's not the same asymptotically. Right? You square something, it's bigger. If that something is monotonically growing. Even the square of the log is bigger than the log. Never mind the square of n or the square of 2 to the n. It gets worse and worse. as you square larger and larger things. You get multiplied by larger and larger quantities. Okay, next theorem. And next theorem is actually so subtle that we'll skip it for now, but we'll prove it in about an hour. Let me show you what it says. It says to get rid of non-determinism in a space bound, it's sufficient to just square the space. You don't need to do more than squaring the space. Because to get rid of non-determinism in time, we had to exponentiate the time. So here, to get rid of this red n is for non-determinism, I'm color coding it red. To get rid of this non-determinism in time, we had to exponentiate the time, raise the time from a base of c. Here, we don't have to exponentiate the space to get rid of the non-determinism. So this is the analog of this theorem. We don't need to exponentiate the space to get rid of the non-determinism. All we need to do is square it. Of course, if you exponentiate it, that's fine too, but you don't need to. And this we can prove. This is not easy to prove, by the way. It's called Savitch's theorem, and that's subtle. This will probably be the hardest theorem we would have proven until now. We're about to prove it. Not just second, but in about half an hour or an hour when we get to it. I have a whole couple of slides just for that. But once you prove this, a corollary of this will show that deterministic polynomial space is equal to non-deterministic polynomial space, and that's why we call it just P-space, because it ignores polynomial or ignores non-determinism or determinism in terms of polynomial space. Because if every non-deterministic class is contained in the square of the deterministic counterpart, all of these are contained in all of these for all exponents k. How many understand the corollary? Okay, good. Of course, we still have to prove this. The corollary would be that. We'll get to that in a second. Okay. Now, as far as deterministic polynomial space classes go and non-deterministic polynomial space classes, it turns out that non-deterministic polynomial space n to the r, the polynomial with exponent r of degree r, is properly contained in a deterministic polynomial n to the r plus epsilon for arbitrarily small epsilon. So as long as you slightly increase the exponent, you can get rid of the non-determinism, it turns out. Okay. And if this was deterministic and this was deterministic, this will be a proper containment. And you can prove that using a padding argument, and I'll leave it at that for now. So here's the Chomsky hierarchy reloaded. So we already know about the regular languages, the context-free languages. Now we know about P and NP, and there they are. And now we know about P-space, right? So P-space contains P and contains NP. And by the way, it's still an open question whether P-space is equal to P. We don't know that. We don't even know if P is equal to NP. But if P-space and P were the same, which is an open question, NP, which is sandwiched in the middle, will be equal to both of them. And then the $1 million prize will be a corollary to that. So if you can prove that P is equal to P-space, which is still an open question after 45 years, a simple immediate corollary of that P is equal to NP, and you collect your $1 million. So P is equal to P-space is a much harder thing to prove even than P is equal to NP, because P is equal to NP is a simple consequence of that. That's still open. So this Venn diagram, not all of these classes are necessarily proper. They're still subsets. P is a subset of NP, and NP is a subset of P-space, true enough. But all these three could collapse into one, and the context-sensitive languages are sandwiched in between them also. Now, some of these subsets are proper. We know that finite languages are a proper subset of the regular languages. Here's a language that's finite. Here's a language that's regular, but not finite. They're both regular. So there's proper containment here. There's also proper containment there. And there's proper containment here. WWR is context-free, but not deterministic context-free. You need non-determinism to recognize that. And there's proper containment there. We know that for sure, right? And languages is A to the N, B to the N, C to the N. We know it's not context-free, but it is polynomial time. In fact, it's linear time. So these are all proper containments. This containment may or may not be proper. That's an open question. This containment may or may not be proper. That's an open question. And therefore, so is this pair of containments here, this and that. Is P equal to P-space. We know that P and EXPTIME are not the same class. We can prove that. We will prove that before we're done today. That P and EXPTIME are not the same class. We'll also prove that polynomial space and exponential space are not the same class again. But this containment may not be proper. We don't know. And this containment may not be proper. We also don't know. These are all open questions. And we'll talk more about that as I'm just bringing it to your attention and what's going on here. So now you can see and understand more of these regions in this diagram, and we'll pile on more regions as we go. Don't want to show you, before it's time, the more complex version of this slide, but it's getting more and more dense and populated with classes. Okay. So a lot of these questions are open. There's a lot more questions than answers in complexity theory, by far. It's not even close. Okay. So a lot of this field was pioneered by Hartmanis and Stearns back in the 60s. And they built on the work of Turing. In fact, their proofs, which we're about to show for some of these theorems, will mimic the proof of the halting problem, for the halting problem being undecidable that Turing put forth in the 1930s. And then 35 years later, they did the same now with a stopwatch in their hand, watching time and space resource consumption. Not just what's possible and not possible, but how quickly you can do things. So this will make heavy use of diagonalization and dovetailing. Okay, we're getting even more mileage out of it now. That's why we harped so much on these techniques earlier in the course, diagonalization and dovetailing, because they're so ubiquitous, so powerful of techniques that they keep occurring again and again. We get a lot of mileage as we go. So we're going to prove about complexity classes the following, that if you have any kind of time bound, linear, quadratic, exponential, whichever one you want, there's always a decidable language that can be decided. It's not undecidable. It's an algorithm that decides it always stops, always halts, but it cannot be done within that time bound. It takes more time than that, asymptotically. So that's an interesting result. This shows that there's no time complexity class in which all the decidable languages reside inside that time complexity class. There's no like super class of time complexity class that contains all the decidable languages. Now, languages are decidable but are outside that time bound. However large you want to make that time bound. And you can make some very large time bounds, right? You can make arbitrarily complicated, horrendously growing, like, n factorial, it grows very fast. But what if you take n factorial, factorial, factorial? Right? That grows even faster. Right? And what if you take 2 to that power? That grows even faster. And put a factorial on top of that. You can just make larger and larger functions. Right? This theorem says that there are languages that are decidable that cannot be decided even in that time. This time is not large enough to decide certain. Now, how do you prove something like this? So this immediately gives rise to an infinite hierarchy of decidable languages. All right? No time complexity class contains all the decidable languages. I mean, that's kind of a monumental theorem. Right? In some sense, it's a negative theorem. And by the way, each time class, how many languages are in a time class deterministic linear time? How many languages are in there? Countably infinite. How many understand that? Why? Don't even go that far. How many distinct different languages are there in linear time, deterministic linear time? That class, how many languages it contains? Different languages, different than each other. 17? 1,000? This is not a hard question at this point, if you understand the definitions. Countable infinite. Why? Yeah, all the regular languages are within deterministic linear time, and there's an infinite number of them. They're all different. End of story. Are there other languages besides the regular languages in deterministic linear? Of course they are. Like 0 to the n, 1 to the n, 2 to the n. It's not even context free, and it's in there too. And there's plenty of others. Okay. Why aren't there an uncountable number then? If we're such on a roll, why not say, well, there's an uncountable number of languages in deterministic linear time? So are there an uncountable number? No. Why not?
You can write grammars for all those languages.
Yes.
You can enumerate the, you can dovetail through the machines that
Yes, you can enumerate the machines. All these languages, because they're decidable, there's a Turing machine that decides each, and the Turing machines are countable. And some of those Turing machines, across all Turing machines, don't yield decidable languages. Some of them can recognize languages which are recognizable but not necessarily decidable. There's plenty of languages which are not recognizable even, but there's no Turing machines for them. So a decidable language has got to be a Turing machine for that always halts. There's only a countable number of Turing machines. There's only a countable number of languages within any given class of decidable languages, whether it's linear time, logarithmic space, exponential time, super exponential space, P, NP, whatever. Are we good on this? Okay. So back to this proof. We're going to prove that there's a language that is decidable, but not within this time bound, no matter what this time bound is. All right. So it's a proof by diagonalization. So we're going to make sure there's some well-defined lexicographic order on the machines. Machine 1, machine 2, machine 3. And you can fix the machines by sorting them by description size, or within size by lexicographic order. But that's some canonical lexicographic order on the machines. And we're going to interpret the inputs also as integers, if you will. Here, all the strings in sigma star are represented as integers by dovetailing. String 1 is A, then B, then AA, AB, BA, BB, AAA. That's the 7th string, and so on. So you can assign numbers to the machines and numbers to the strings, just so you know we're good on that. Now here's the language we're going to prove is decidable, but not within time t of n. Define this language to be all strings I, is the integer, or the integer representation, such that machine I does not accept the input I within time t of I steps. Okay. So L is decidable. How do you decide L? Well, if I comes along, how do you decide? Well, from the canonical ordering, the dovetailing ordering of the Turing machine, figure out what the ith machine is. You're the simulator. And then simulate that machine I on that input I that was handed to you. And simulate it only for t of I steps. And then accept, if and only if, that machine m sub I does not accept I within time t of I. That's the only time you accept I. Otherwise, you reject I. So I just described to you how to decide this language, always in finite time and always correctly. Now, that simulation cannot be run in time t of I. Why? Why is the language L not in deterministic time t? Because we'll assume towards contradiction that there exists some Turing machine, call it m sub k, and the index is k of that machine in this canonical ordering. That machine m sub k decides L, and does it within time t. Okay? And once you have this machine m sub k, it decides or accepts L. So what we're going to do is take this machine, and I just copied it over here at the top of this slide so you don't have to go back and forth between the two slides. Take this machine m sub k that decides L and feed its own index to itself. Run it on its own index k. So run m sub k on k. So if k is in the language L, m sub k must accept k within time t of k, right? And if it accepts it, then this branch of the if statement will get invoked, and then m sub k will then reject k, right? So you're seeing diagonalization here kind of rear its ugly head, and this argument parallels the undecidability of the halting problem theorem, right, by Turing. Now, on the other hand, if k is not in L, m sub k must reject, within that time bound, must reject k, but if it rejects k, the else will be fired, and then it will accept. So basically, we have a contradiction here. right? The contradiction is that K is in the language L if and only if it isn't. And that's a contradiction. You have a preposition P, such that P if and only if not P. And that means you have a contradiction and the assumption was false. And that's, of course, is also Russell's paradox. That's basically a form of diagonalization here. This mimics Turing's proof of the undecidability of the halting problem. There's Pinocchio saying, my nose will now grow. And he can't be lying and he can't be telling the truth. Right? So we've seen this situation before. And what was our assumption? The assumption was that this machine can decide L in time t of n. L is decidable. We already said that up here. L is decidable by simple simulation, right? But it's not decidable within that time bound. So another way to think about this argument is more pictorially. So I'm going to put it in a table for you so you actually see the diagonalization right in front of you, kind of graphically, visually, rather than just to mention it algebraically instead of geometrically. So here are all the strings in sigma star enumerated. String 1 is A, string 2 is B, then AA, AB, BA, BB, AAA, and so on. These are all the strings in sigma star and their numbers. These are all the Turing machines that run in the T of n time bound. Right? And by the way, how do you get a Turing machine to respect the T of n time bound? You can run the machine, and as you run the machine, it's an arbitrary machine, and whether it runs in that time bound or not is undecidable. But you can make this machine run within that time bound and artificially abort it and stop its execution when the time bound is reached. It won't necessarily be the same machine running the same function as before, but at least this machine will respect the time bound. Otherwise, you'll be chopping it short before it can exceed the time bound. How could you do that? Every time it changes the state, click a counter up. And click the counter up again every time it changes another state. Every time it makes a move, you count. And when a count exceeds T of n, you make it stop. And if it didn't accept before then, you declare it a rejection, and that's it. So here are all the time-bounded Turing machines, all of them. They're all T of n time-bounded Turing machines. This green checks and red X's tell you whether this machine M sub I will halt on this string J, and check means it will halt and accept. X means it'll halt and reject. So the X's are rejections, the green checks are acceptances. In either way, it always halts because it's time bounded. After that time, it always halts. Or even before that time. It never exceeds that time. Right? So a quadratic algorithm doesn't have to take as much as quadratic time, but it certainly can't take any more. Right? I mean, even bubble sort can sometimes run in linear time, even though the worst case is quadratic. When will bubble sort run in linear time? When it's already sorted, and even some other cases. So it doesn't have to take that long, but it never takes longer than that. So all these machines are time-bounded by T of n, and this is what the results are of these machines. So what do you think we're going to do next? We're going to diagonalize. So we're going to go down the diagonal and construct another machine here that basically, for input I, simulates the ith machine and does the opposite. So if this is an accept, this becomes a reject. If this is a reject, it will accept the second input, right? So this machine M prime sub 2 will run the second Turing machine on the second input and do the opposite of what the second machine of this machine here did on the second input, which was a reject, and therefore will deliberately do the opposite, be contrary, and accept, and so on and so on. So we're going down the diagonal doing the opposite, and this machine here is computing a decidable function. All it's doing is going into one row of the table and one column of the table, where the row and the column have the same index, namely its own input, and then simulates that machine on that input, and then does the opposite. These machines will always halt, and always halt within that time bound. And so this machine here, if it runs within that time bound, it should be in the table, but it isn't. So it can't be running within the same time bound. But it is decidable, because there's nothing undecidable about this machine running and doing this job. It'll just take more time than t. Okay? So basically it shows you that there's a function that's decidable that's not t-bounded, not t-time bounded. And again, here you can see the diagonalization. Here, in the previous slide, it was more implicit. But that's still diagonalization. And here it is more explicitly. There's Cantor smirking. It's his gift to us. You see how much mileage that single concept begets us. It's a lot of, there's hundreds and hundreds of different theorems where diagonalization is applied, mathematics and complexity theory and theory of algorithms and dovetailing, same thing. Pigeon-hole principle, same thing. It appears in many, many places. Very powerful concepts. Relatively simple when you think about them, but very powerful consequences when you apply them properly. Okay, any questions about that? Yeah.
Does this mean that can you still have like a set of Turing machines that are in D-time? Like even if you exclude some of these, that was not.
Well, so let's parse that carefully. D-time is not Turing machines; it's languages. So you want to rephrase the question without a type error. All these complexity classes contain languages, not machines. So what is your question now? Well, all of these languages are in T of n. And so any subset of them will also be in T of n, right, trivially. But here we're listing all of them, like this. So because because the answer to your question was simple, I'm not sure if I answered your question or whether what you said was really what you meant to ask. But anyway, you can think about it some more, and we'll get back to it. Yeah, question. Stop right there. There are no uncountable infinite number of machines, right? Number of machines is countable. So we can say that, it won't be true. So you want to continue or rephrase? Okay, we'll come back to that. I know this is tricky. This is tricky business. So what are we doing here? We're regurgitating the proof of the halting problem, right? Except now we're watching the clock while we're doing this. There's an extra thing going on. We're trying to be conservative in how much time we're using when we're doing the halting problem proof for showing that the halting problem is undecidable. So this is a very similar structure to that proof, except now we're watching the time like a hawk. So there's extra layer of kind of complication involved when this is happening. And next we'll do the same thing for space. Right now we did this for time. We'll show immediately next, before we even take a break, because that's the very thing that's followed, that this theorem applies for space as well. In other words, there's no space complexity class that contains all the decidable languages. Some decidable languages must take more space than whatever bound you care to name, even a huge bound like that. That's not enough space for some decidable languages, which is amazing, actually. I mean, you can write very large, fast-growing functions. They're just not large enough. You can use tetration, which is a generalization. How many? No, tetration. That grows even hugely faster than exponentiation. That's not enough space or time for some decidable function. So they're not undecidable. They're perfectly decidable. They just need enormous amounts of space or time to decide. Yeah.
So I have two questions. What is n here?
N? Yeah. N is the input size. So it's the length of W. W is the input string to whatever machine you're running.
And it's T of n? Is that like a fixed function? It's not asymptotic?
It's a fixed function, but we kind of write it asymptotically. It's like big O. So these time complexity classes are defined with a big O kind of in mind. We don't care about the constants. Yeah. Because constants depend on The constant, here's why we don't care about constants. There's several reasons. One is they're usually small. They're usually 2 or 3 or 5. Not a big difference. When you talk about polynomial versus exponential, a factor of 2 is insignificant. Right? When you talk about a million or 2 to the million. 2 to the million is so far away from a million that there's no point saying, oh, wait a second, what about 2 to the million versus 3 million? 2 to the million versus 10 million? It's still hugely so much more than any of these that the constant doesn't matter. Second reason, asymptotically speaking, your smartphone is the same speed as an abacus. How many believe that statement? What allows me to make this statement? I mean, your smartphone can make a billion calculations per second. So can your Dell laptop or Dell desktop computer. Why is your Dell desktop or even a cloud supercomputer, all of the Amazon AWS, the entire Amazon cloud, asymptotically speaking, it's the same speed as an abacus, the thing with the beads that you just flip the beads around. Don't get me wrong, I'm talking about a really big abacus. But still, abacus is roughly an operation of 2 or 3 per second. Even really fast abacus operators can operate more than a few per second, right? I assume. How many have used an abacus in their lives? It's kind of cool, right? Sometimes you can do it for fun. Okay. Why is the Dell cloud or the Amazon cloud or the entire Google infrastructure cloud the same speed as an abacus, asymptotically speaking? They use the same computing model?
They go at the same
Yeah, they have the same rate of growth. The constant is not the same. But if you want to add 2 numbers with an abacus, if you want to add 2 numbers with the Google Cloud, or even 1 million numbers, or even 1 trillion numbers, asymptotically it'll be the same speed. The constant will be very different. What will be the constant difference? Roughly, between an abacus and your Dell desktop. How much? Trillion? So this runs at trillions of things per second, roughly? I mean, it's not far off, but how many additions or multiplications per second can these computers on your desk can do, roughly? So they're running at 2 gigahertz, 3 gigahertz, 1 gigahertz. How many operations per second is that? About a billion, right? Not a trillion. Trillion is, how many zeros in a billion? Quick. 9. But you said it quickly. You get points for quickness. That's good. And a trillion, how many zeros? Quick. 12. And how many zeros operations per second can this do? Roughly 9, and not even quite 9, because 9 presumes that every cycle of this 3 gigahertz it can do. It's not quite that. It needs several cycles per, so maybe 8 zeros, not 9. Maybe you can do 100 million or 500 million, not quite 3 billion or so. Anyway, difference speed between an abacus and one of these is about 1 billion to 1, right? Or 100 million to 1, billion to 1, let's call it. That's just a constant. And I say the word just in air quotes. It's a big constant. In practice, it makes a big difference. But in theory and asymptotically and big O notation, that constant vanishes. Okay. So that's sort of a long answer to your shorter question from earlier. Yeah. So the constant is, even though it could be arbitrary, for that machine it's fixed, right? So it could be run in 2n squared time, or 10n cubed time, or something, So we talk about these time complexity classes sort of ignoring the constants, but when the machine actually runs, you have to fix the constant at something. There's a particular constant that you can hardwire into the, cutoff time that aborts it after a certain number of operations. So it's whatever it is for that particular machine. So when you say T of I, it's not big O of T of I. Here it's literally some function T. So T could be 3x squared or 3n squared, I guess, here. So here the constant could be 3. And that's what's hardwired into, the rest of the argument. Now, when we talk about time and space complexity classes, d time 3n squared is the same as d time 5n squared, asymptotically speaking. We don't distinguish between those, although you could, strictly speaking, you could make that distinction too. But usually we bunch together all the languages that can be recognized asymptotically within time t of n. So it's the asymptotic that we're kind of after, not the constant. But when it comes right down to simulating things, the constant is there hardwired. And if you want a bigger constant, fine, use the bigger constant. But you don't get a bigger constant than that. You can't just keep increasing the constant. Then it's no longer a constant. The constant that keeps increasing is the name for it. It's called a function, not a constant. It's a monotonically increasing function or a changing function. The constant doesn't change. But you can choose whatever constant you want. Same as if we talk about quick sort and merge sort and heap sort. So we talk about sorting algorithm and we say, oh, bubble sort is n squared and merge sort is n log n. You don't stop and say, oh, wait a second. Is it 2n squared or 3n squared for bubble sort? You don't really care. It could be 5n squared. It could be 1.5n squared. What you care about is it's n squared. And that merge sort is not. It's n log n. And you don't say, wait a second, it's n log n, but is it 20n log n? Maybe it is. Maybe it's only 3n log n. But that's not so much the point. The point is it's n log n. The other one's n squared. And you compare the asymptotics. Now, don't get me wrong. I'm not saying asymptotics never matter. Because if you come up with an algorithm that's n log n, but it's a Google n log n, and a Google is a constant, it's a very large constant, 10 to the 100, you're much better off with an algorithm that's 5n squared than a Google n. Even though one is quadratic and one is linear, technically speaking, asymptotically speaking. You're much better off with the quadratic with a small constant than with the linear with a huge constant that's out of this universe. How do you understand that in practical terms? That's true. Asymptotically, one is still quadratic, one is still linear. Okay? But usually in real life, constants are not as large as a Google, or even 10 to the 10 usually, or even a million. That's a very large constant in practical terms. Okay. Now, having said all that, in algorithms, if you can get an algorithm to run in time f of n, and the constant is large, there's probably some other clever person that will reduce that constant to a small, tiny portion of what your constant is, and somebody will even do that to them until the constant gets really small, like 2 or 3 or 5 or something. And there's many, many examples in algorithm design that are like that. So that's another reason why not to worry about constants, because those could be tamed usually. That's usually what happens. Yeah. Yeah, and that happens too. And then you have to kind of pick your poison. Do you want to, large constant and a smaller exponent, or, larger exponent? It depends on the problem size and exactly what the other considerations are. And hopefully it's a smooth trade-off, so you can pick your favorite point on the curve. Right? And in real life, we do this all the time. Right? For example, when you buy airline tickets, you can fly first class, and it'd be a direct flight, and you have a big sofa cushion bed that you can sleep in, for 15 hours of the flight. But it'll cost you $10,000 if you do this, or whatever. So you can trade off comfort against cost, dollar cost. You do this all the time when you rent an apartment. You get a very nice, large, cushy apartment with a beautiful ocean view, but you're going to pay through the nose, and is it worth it? On the other hand, if you live in a tent on a sidewalk, you'll pay very little, but you don't even have a bathroom. So we all pick points along this trade-off curve of how much we want to pay and what we get back for that value, right? We do this all the time. You even do this in dating, actually, in relationships, in marriages, trade-offs all over the place. I'll leave it at that. Use your imagination. So yeah, that can happen too. Okay, so again, this is Turing's proof of the halting problem undecidability, except here it's all decidable, and instead we watch the clock, and when we do that, some interesting things happen, and we just show that no time or space bound, or at least no time bound can cover all decidable languages. There are ones that require more and more and more time to decide, even though they're all decided. That was not known to Turing. That was not developed until the 1960s, late 60s, early 70s. Any other questions so far? So now we can do the space analog much more quickly than before, because all the same techniques, and in fact the proofs will be almost identical for the space version. Now we've seen the time version. So the space complexity hierarchy, again, there's Hartmanis and Stearns, who are responsible for pioneering this whole area of complexity theory. And this theorem says that for any space-bound S of n, there exist languages that are decidable but are not within that space. In other words, no space complexity that contains all the decidable languages, and that there are decidable languages that take arbitrarily more space to decide, like this big growing function here with all these factorials and exponentials. Some decidable languages take at least that much space and more to decide. And they're not undecidable. They're perfectly decidable. There's algorithms for them which always halt and always give the right answer. But even the fastest of these algorithms will take more than that, space or time. All right. Again, diagonalization, and you can see the similarities to the previous proof. We lexicographically order all the machines, lexicographically order all the strings, and then we define the same language as before, except now with the space constraint. The language is L containing all I is such that the ith machine does not accept the ith string within S of I space instead of T of I time. Okay, so obviously it's decidable. There's one little hitch here that's different than the previous proof. You want to simulate this, you want to decide it by simulation. So you get I handed to you. You're the decider for L, so what do? You find the ith machine, M sub I, and then run it on the ith string, on I that was given to you, and then you see how much space it uses. And if it ever exceeds that space, you reject. If it rejects within that space, you reject. If it accepts within that space, well, if you reject within that space, you accept. If you accept within that space, you reject, because you got to do the opposite. You got to do the opposite of what this machine, the ith machine, does, M sub I. Now, here's the catch, the hitch. You're simulating something that uses no more than a certain amount of space. And we already said about an hour ago that if you compute within that space bound, you can compute and compute and compute and compute forever within the same space bound, never exceeding the space bound. So you're the simulator. You have to keep an eye on this situation. And if it's trying to compute for too long within that space bound, you know it's in an infinite loop. And how long is that? Exponential time. By the pigeon-hole principle, if you take too long and you still remain within the same finite amount of space, you must repeat yourself by the pigeon-hole principle. And you're the simulator can see if you repeat it by keeping track of this giant long audit trail of previous states, and every time you change the state to something new, see if it was already been there before, and if it did, you know you're in infinite loop, and then you can stop and do the right thing. So the simulation always halts, which means this is a decidable language. L. I just described to you how to decide it. That's what I mean by infinite loops here. That's a little caveat on the simulation. When it came to time, we didn't have to worry about infinite loops, right? Here's the previous theorem with time. We just simulated it. It was not worry about infinite loops over here. Why? Because if you just watch the time, you watch the clock here, when that time bounding is exceeded, you know the clock, the alarm sounds, the stopwatch rings, and then you can stop the whole thing. But here in this new theorem, you can't do that. You have to worry about infinite loops, and you do that by watching the clock again while you're simulating within that space bound. And if the clock exceeds a certain number, infinite loop is guaranteed by the pigeon-hole principle, because it's deterministic. Right? So it is decidable, but is it within this space class, the deterministic space S? Again, the rest of the proof is similar to what we had before. Assume towards contradiction that it is in that space bound, and then take some Turing machine within that space bound and have it decide L. If it's decidable, that there's the machine for it, M sub k, and k is the index of the machine that decides L, and assume that M sub k runs in time in space t of I or t of n, and if so, consider whether you feed it to itself, what will it do, and if its own index is an element of the language, it'll do the opposite, which is what it's designed to do. It's kind of being contrary. So if k is in the language, it'll reject it, which means k is not in the language. And conversely, if it's not in the language, then it must reject it. But if it rejects it, then it is in the language, because the else will kick in, right, out of here, and then it must accept by definition. And so its index is in its own language if and only if its index is not in its own language, this machine M sub k, which is a contradiction, which means it's not within that space bound. It takes more space to decide it than that we have. And again, Cantor is smirking and Pinocchio's displaying Russell's paradox and so on. So very similar proof to what we did before. And that shows us an infinite space hierarchy of languages that require more and more and more space to decide. And of course, you can couch it like we did before in this nice geometrical diagonalization picture, right? Here are all the machines that are space bounded, S of n space bound. Here are all the strings in sigma star, and these are all the space bounded machines. Here's what they do: accept, reject, on the various strings. They always halt because all these they all have decidable languages that they accept. And then you can go down diagonal and construct a language that's not equal to any one of these, but it is a decidable language, because you can run the appropriate machine given the input I and see what it will do on the ith input when you run the ith machine on the ith. And so by simulation you can do this. The simulation, though, will take longer because this is a decidable language not equal to any one of those things in the table. And so it's not in the table, which means it's not S of n space bounded, right? And so some functions require more than S space to compute them, even though they're perfectly decidable, perfectly computable. There's nothing uncomputable or undecidable about them. Yeah. Yes. Yeah. It's a very good question. This is called axiomatic complexity theory, and Manuel Blum in the early 70s showed that as long as your resource satisfies two simple axioms, all these hierarchies immediately arise. That the other resources can include bit changes, power consumption, cache misses, page faults to disk, messages sent over the internet, whatever the resource is that you're watching. And these two axioms are very simple. If you compute longer, the resource you're using will be monotonically increasing. That's one of the axioms. Very, very straightforward assumption. You're not going to be using less of the resource if you compute more. Either you use the same amount or more, not less. That's true of space, of time, of page faults, of message sending, of power consumed, whatever. And there's another simple axiom. And once you satisfy these two axioms, all these automatically fall out as results. So it's not just about space and time. And you can see the pattern, how simple, how similar the space argument was to the time argument. It's all basically diagonalization, dovetailing, and occasionally the pigeon-hole principle. Okay, so, and we'll get to that. All right, and this brings us to Savitch's theorem. And here we're going to show that to get rid of non-determinism in space and make deterministic computation, it suffices to at most square the amount of space to make it deterministic, not exponentiate like we did with time. Okay, space. So this is the P is equal to NP theorem, but instead of for time, it's for space. And because this is not easy to prove, we'll prove this. We'll take the break first, and then right after the break, we'll prove this. It's really a beautiful theorem. It makes really heavy use of the reusability of space. We reuse space extremely aggressively here, at the expense of time, but we conserve space. And I'll give you a little kind of preview of what this looks like. It's actually 2 slides long. All right, any quick questions before we take a break? Yeah. It's only if they were both subsets of each other, they'll be equal.
Yeah.
They're not necessarily equal. No. Yeah. For certain f's, they may be, but for other, in general, they're not. There's another theorem that shows that their functions are so weird that for certain functions, this complexity and that complexity are the same. In other words, it doesn't buy you any extra. But those are kind of pathological functions. The functions themselves are not computable. Time and the space functions themselves are undecidable, uncomputable, but they exist. And when they do, all sorts of collapses of classes can happen. But because they're not computable, they're almost useless as resource bounds. And some of them are not even described finite, but they do exist. But that's a whole can of worms that we don't want to quite open here. But feel free to read about it for extra credit. It's out there. All right, let's regroup in about 15 minutes and keep going.